What if everything we thought we knew about space was wrong? For centuries, we've looked up at the night sky and built our understanding of the cosmos on what we could see and measure. Planets orbiting stars, galaxies swirling in predictable patterns, the laws of physics holding everything together. But what if the universe is far stranger, far more mysterious than we ever imagined? What if some of the most fundamental rules we rely on are being broken right before our eyes? Recent discoveries in astronomy are turning established science on its head, revealing a side of space so bizarre, so utterly unexpected, that it challenges not just what we know, but how we think about reality itself. Imagine gazing into the depths of space and finding worlds that wander alone in the eternal dark, untethered to any star. Picture cosmic structures so immense they shouldn't exist according to our current models, or energies so powerful they defy explanation. These aren't ideas from science fiction, they're real, documented phenomena that astronomers are scrambling to understand. Every day, new data pours in from telescopes and probes, each revelation more puzzling than the last. It's as if the universe is slowly pulling back a curtain, showing us glimpses of a reality far wilder and more wonderful than we ever dreamed. And that's exactly what we're diving into today. In this video, we'll explore 30 of the most astonishing space oddities recently uncovered by scientists, from rogue planets drifting through the void to cosmic anomalies that seem to break the very laws of physics. Each one is a reminder that we are still at the beginning of this incredible journey of discovery, humbled by how much remains unknown. This isn't just a list of facts, it's an invitation to wonder, to question, and to feel that same spark of curiosity that drives humanity to look up and ask what's out there. So settle in, open your mind, and get ready to see the universe in a whole new light. Our journey into the cosmic unknown begins with a celestial paradox, an object of immense darkness that somehow creates light. The Hubble Space Telescope recently captured something that should be impossible: a supermassive black hole with a mass equivalent to 20 million of our suns, hurtling through the void of intergalactic space. But this isn't just any rogue object. As it travels, it's not consuming everything in its path. Instead, it's acting like a cosmic farmer, plowing through clouds of gas and leaving behind a 200,000 light-year-long trail of newly ignited stars. Picture the sheer scale of this for a moment. That trail of newborn suns is nearly twice the diameter of our entire Milky Way galaxy, a brilliant scar across the darkness. This black hole is moving so fast that it could travel from Earth to the Moon in just 14 minutes. The forces at play here are almost beyond comprehension. Normally, we think of black holes as the ultimate consumers, lurking in the centers of galaxies and pulling everything into their gravitational grasp. This one, however, is an outlier, a rebel. It's not sitting at the heart of a galaxy, it's running from one. So how does something with so much gravity get evicted from its own home? Astronomers believe the most likely explanation is a violent cosmic game of billiards. When two galaxies merge, the supermassive black holes at their centers eventually sink toward the middle of the new combined galaxy and begin to orbit each other. If a third galaxy joins the mix, bringing its own black hole, the gravitational interactions can become incredibly chaotic. In this turbulent dance, one of the black holes can be slingshotted outward at tremendous speed, ejected from the galactic core entirely. This discovery fundamentally challenges the long-held belief that these colossal objects are permanently anchored to the centers of their galaxies. It suggests that there is a population of runaway supermassive black holes wandering the darkness between galaxies, invisible to us unless they create a spectacular signature like this star-forming wake. It forces us to reconsider the dynamic lives of these enigmatic objects and opens up a new field of study into what happens when the most powerful engines in the universe are set adrift. But if a rogue supermassive black hole challenges our ideas of cosmic order, the next discovery fundamentally questions the very uniformity of the universe itself. Astronomers have identified a structure so incomprehensibly large that its existence seems to defy one of the most fundamental tenets of modern cosmology. Known as the Giant Arc, it is a near-perfect crescent-shaped arrangement of galaxies, galaxy clusters, and vast clouds of gas that stretches an astounding 3.3 billion light-years across the sky. To grasp that scale, consider this. If you could travel at the speed of light, it would take you over 3 billion years to go from one end of this structure to the other. It is not merely an object in space, it is a feature of the cosmos, a thread in the fabric of the universe that should not, according to our best theories, be there. This discovery directly confronts what is known as the cosmological principle. This is the assumption, central to the standard model of cosmology, that on a sufficiently large scale, the universe is homogeneous and isotropic. In simpler terms, it means the universe should look roughly the same in every direction, and that matter should be spread out fairly evenly when you zoom out far enough. There shouldn't be any privileged location or direction, and there certainly shouldn't be structures that are a significant fraction of the size of the observable universe itself. The Giant Arc, representing a massive deviation from this assumed smoothness, throws a wrench into this foundational idea. It's like looking at a vast, sandy beach and finding, from a high enough vantage point, that the grains have arranged themselves into a single, deliberate pattern stretching from one horizon to the other. The statistical improbability of such a structure is staggering. Cosmologists use complex models to predict how matter should be distributed after the Big Bang. These models do allow for some large-scale formations, but the Giant Arc is so immense that it lies far outside the predicted upper limit for such structures. Its sheer size and coherence suggest that either our understanding of the initial conditions of the universe is incomplete, or that there are forces and processes at work on the largest scales that our current physics does not account for. It forces a profound question. Is the universe truly the same everywhere, or are we living in a cosmos that is fundamentally lumpy and textured in ways we are only beginning to perceive? This isn't just a new object to catalogue, it's a potential crack in the very foundation of how we understand reality. From the vast, cosmic structures that challenge the nature of reality itself, we zoom into a single, bewildering world that defies everything we know about what a planet can be. Imagine a planet so incredibly light and fluffy that if you could find an ocean large enough to place it in, it would float. This isn't a thought experiment. It's a real place called WASP 193b, and its existence has left astronomers utterly perplexed. Located over 1,200 light-years away, this exoplanet is roughly 50% larger than our Jupiter. But here's where the comparison ends and the mystery begins. Despite its colossal size, it has a density so absurdly low it's been compared to cotton candy. In fact, its entire mass is only about 140 times that of Earth, meaning it's over 1,000 times less dense than Earth's atmosphere. It is, by a significant margin, the second least dense planet ever discovered. The numbers alone are difficult to comprehend. To have such an enormous volume with so little actual stuff inside it forces a complete re-evaluation of planetary formation. Normally, gas giants like Jupiter have a dense, rocky, or metallic core that acts as a seed, gathering immense amounts of hydrogen and helium gas from the primordial disk around a young star. WASP 193b appears to have almost no core at all. It's essentially a gigantic, puffy atmosphere held together by the faintest of gravitational pulls. The planet completes a full orbit around its sun-like star in just 6.25 days, and this close proximity bathes it in intense radiation, which should theoretically heat its atmosphere to the point of rapid escape. According to our current models, a planet with so little gravitational hold shouldn't be able to maintain an atmosphere against such stellar fury. It should have been stripped down to a bare core billions of years ago. And yet there it is, a cosmic cotton ball, stubbornly and inexplicably intact. This presents a monumental puzzle for planetary scientists. How does such a world form, and more importantly, how does it survive? One leading theory suggests it might have formed much farther out in its solar system, where temperatures are colder and icy materials can accumulate into a large but very low-density core. A gravitational tug-of-war with another planet or a disturbance in the system could have then sent it migrating inward to its current scorching orbit. Once there, the intense stellar radiation would have inflated its already puffy atmosphere to the bloated proportions we see today, like a balloon expanding in the heat. But this still doesn't fully explain how it holds onto that atmosphere against the relentless solar wind. Unraveling the secret of WASP-193b isn't just about solving the riddle of one oddball world. It's a key that could unlock new chapters in our understanding of atmospheric physics and the incredible diversity of planets that the universe is capable of creating. It shows us that nature's imagination is far greater than our own, crafting worlds from the faintest wisps of gas that somehow endure against all odds. Just when we thought the cosmos couldn't present a more baffling contradiction, astronomers stumbled upon a ghost. Not a ghost of light or sound, but a ghost of a galaxy. A vast, swirling island of material that appears to be almost entirely empty. This is J0613+52, a dark, primordial galaxy discovered entirely by accident. While surveying the sky with powerful radio telescopes, scientists detected the unmistakable signature of hydrogen gas, the fundamental fuel for star formation, moving in a way that indicated it was bound within a massive rotating structure. Everything about the motion pointed to a galaxy, but when they turned every optical and infrared telescope they had toward that same patch of sky, they found nothing. Absolutely nothing, no starlight, no glowing clusters, just the profound, empty blackness of intergalactic space. This invisible behemoth, located roughly 300 million light-years away, is a galaxy in its most basic, raw form. It is made almost entirely of interstellar gas and, we must assume, an enormous amount of the universe's most mysterious ingredient, dark matter. The rotation speed of the gas reveals the galaxy's tremendous mass, but with virtually no stars to account for that mass, the only explanation is that it is overwhelmingly composed of this invisible gravitational glue. It is a dark matter galaxy that has, for reasons we don't yet understand, failed to light up. It's a cosmic blueprint that was never built upon, a potential that was never realized. This makes it a fossil, a pristine relic from the early universe that has somehow survived for billions of years without undergoing the star-forming fireworks that define every other galaxy we've ever seen. The significance of this discovery cannot be overstated. J0613+52 offers a direct, unaltered window into the conditions of the primordial universe. In the standard model of galaxy formation, dark matter forms first, creating vast halos whose gravity then draws in ordinary gas. If the gas becomes dense enough, it fragments and collapses to form stars. This dark galaxy suggests that for this process to ignite, something more is needed. Perhaps a trigger like a collision with another gas cloud or a shockwave from a nearby supernova. Without that initial spark, a galaxy can remain forever dormant, a silent, dark universe unto itself. Finding this object was a 1,000,000-to-1 accident, which implies there could be a vast population of these dark galaxies floating all around us, invisible and undetected, making up a hidden architecture of the cosmos we never knew existed. Yet, even as we contemplate these dark, silent giants, the universe presents us with a phenomenon that is their polar opposite in every way, not an absence of action, but a spectacularly violent and strangely cold ending. If a dark galaxy is a portrait of cosmic silence, then the Boomerang Nebula is a symphony of stellar death, and it holds a record that is almost impossible to break. This beautiful, bow-tie-shaped cloud of gas is officially the coldest known natural place in the entire universe, registering a frigid 1 degree Kelvin. That is just a single degree above absolute zero, the theoretical point where all atomic motion ceases. To understand how profoundly cold this is, we must look at the vacuum of space itself. The background temperature of the universe, the leftover warmth from the Big Bang, is a steady 2.7 Kelvin. The Boomerang Nebula is significantly colder than the empty space that surrounds it. This defies our basic intuition about how energy works. We typically associate the death of a star with immense heat and a brilliant explosion like a supernova. But here, a star is meeting its end not with a bang, but with a deep cosmic chill. The secret to this incredible cold lies not in inactivity, but in a specific and violent type of activity. At the heart of the nebula lies a dying red giant star, a star similar to what our own sun will become in billions of years. This particular star, however, is in the process of shedding its outer layers at a truly astonishing rate. It is ejecting mass at a speed of nearly 164 kilometers per second, which is about 10 times faster than what is typical for this kind of stellar object. This creates an effect similar to the one we feel when we blow on our hand with pursed lips. The fast-moving air feels cooler than the air from an open mouth because it expands rapidly and cools down. The Boomerang Nebula is the ultimate example of this principle, known as adiabatic expansion. The star's supersonic wind is expanding into space so rapidly that it cools itself down to a temperature even lower than the cosmic microwave background. It's a cosmic refrigerator built by the ferocious winds of a dying sun. This presents a significant challenge to our models of stellar evolution. While we understand the basic mechanics of adiabatic cooling, the extreme scale and efficiency of this process in the Boomerang Nebula are unparalleled. It suggests that the final stages of life for certain types of stars can be far more dynamic and complex than we previously believed, capable of engineering conditions in space that we once thought were impossible to achieve naturally. This nebula is more than just a pretty picture. It is a natural laboratory demonstrating the extreme physics of expansion and cooling on a scale we can scarcely replicate, showing us that even in death, a star can teach us new truths about the universe. But just as we begin to map the familiar stages of stellar death, the universe presents a phenomenon that is utterly unfamiliar, a set of celestial fingerprints that have no clear origin. Scattered across the radio sky are enormous, ghostly rings so vast they could easily contain entire galaxies within their bounds. These are the odd radio circles, or ORC, and they represent one of the most perplexing mysteries in modern astronomy. Discovered only in 2020 by the Australian Square Kilometre Array Pathfinder telescope, these objects are completely invisible to optical, infrared, and X-ray telescopes. They exist only in the radio spectrum, appearing as immense, perfectly circular disks that defy any simple classification. The scale of a single ORC is almost incomprehensible. They can span 1 million light-years across, meaning light itself would take 10 times the age of our entire human species just to travel from one side to the other. To find something of that magnitude that simply wasn't seen until now is a humbling reminder of how much we have yet to discover. Initially, astronomers wondered if they were some kind of instrumental glitch or artifact, a phantom generated by the data processing itself. But as more of these circles were found, their reality became undeniable. They are out there, and we have no definitive idea what they are. Theories, of course, abound, each one more fascinating than the last. One leading hypothesis suggests that ORCs could be the colossal shockwaves from a cataclysmic event in the distant past. Perhaps they are the aftermath of two supermassive black holes merging, sending a spherical tsunami of energy rippling through the intergalactic medium. Another idea posits that they are the throats of hypothetical wormholes, their circular mouths presenting a structure we are only now able to detect. There's even speculation that they could be the immense jets of a central galaxy, viewed end-on so that they appear as a perfect ring to us. What makes ORCs so stubbornly mysterious is that they don't neatly fit any of these models. If they were shock waves from a central explosion, we would expect to find an energetic source at their heart, a galaxy disrupted by a tremendous burst of star formation or a quasar. But in many cases, the galaxies at the center of these rings appear perfectly normal, quiet, and undisturbed. The wormhole theory, while thrilling, remains entirely within the realm of theoretical physics for now. The simple truth is that ORCs don't match the profile of any known object or event. They are a new class of phenomenon, a blank space on our cosmic map that is forcing radio astronomers to go back to the drawing board and question fundamental assumptions about what can and cannot exist in the depths of space. While the ORCs present a mystery on a galactic scale, proving that enormous structures can still escape our understanding, sometimes the most profound puzzles are found in the most compact objects. Deep within our own galaxy lies a stellar corpse that is breaking all the rules, a neutron star known as Swift J1845.00267. To the unaided eye, it would appear as nothing more than a faint speck, but to astrophysicists, it is a screaming contradiction in the void. This object possesses a magnetic field of such staggering intensity that it defies every existing model of how matter behaves under the most extreme conditions imaginable. Neutron stars are already the universe's ultimate extreme physics laboratories. They are the crushed cores left behind after a massive star goes supernova, packing more mass than our sun into a sphere no wider than a city. A single sugar cube-sized piece of this material would weigh as much as a mountain, but even among these incredible objects, Swift J1845 is an outlier. Its magnetic field is measured to be over 2.7 times 10 to the 15th Gauss. To put that incomprehensible number into perspective, the most powerful magnets ever built on Earth, used in MRI machines, reach about 1.5 Tesla, which is 15,000 Gauss. The Earth's own protective magnetic field is a mere half a Gauss. This neutron star's magnetic field is a quadrillion times stronger than our planet's. It exists in a realm so extreme that the very physics we use to describe the universe begins to break down and falter. This places it firmly in the theoretical category of a magnetar, a rare and volatile class of neutron star known for their colossal magnetic fields. But even for a magnetar, this measurement is pushing the very limits of what was thought to be physically possible. The leading theory of neutron star structure, known as the equation of state, describes how matter behaves at these insane densities. It predicts a tipping point, a maximum magnetic field strength that a neutron star can sustain before it becomes fundamentally unstable. Beyond this threshold, the magnetic forces should overwhelm the immense gravity holding the star together, literally tearing the star apart in a catastrophic event. Swift J1845 is dancing right on that razor's edge, and its mere existence is forcing physicists to question if that theoretical limit is wrong, or if our entire understanding of the equation of state needs a radical revision. The implications of this are monumental. This isn't just about adding a new record holder to a catalog, it's about probing the fundamental laws of nature. The magnetic field around this star is so powerful that it warps the very vacuum of space around it, affecting how light travels and even influencing the behavior of subatomic particles. It creates an environment where matter is forced into exotic states that cannot be replicated anywhere else, not even in the largest particle colliders on Earth. By studying the X-rays and gamma rays screaming from this object, we are essentially conducting a unique experiment in high-energy physics, one engineered by the universe itself. Each pulse of radiation is a data point from a realm where protons and neutrons are squeezed into bizarre shapes and where new, unknown particles might briefly flicker into existence. Cracking the code of this impossible star could lead us to a new, more complete theory of matter, one that finally unifies the forces governing the incredibly small quantum world with the immense forces that shape the cosmos. If the ghost galaxy J0613+52 represents the ultimate dark matter-dominated universe, then its polar opposite is a discovery that is, in many ways, even more shocking. For decades, the existence of dark matter has been a cornerstone of cosmology, an invisible scaffold thought to be absolutely essential for holding galaxies together. Without its immense gravitational glue, our models suggest that the rapid spin of a galaxy would simply cause it to fly apart, flinging its stars into the void. This is why the discovery of NGC 1052 sent such a profound tremor through the world of astronomy. Here was a large, fully formed galaxy that appeared to have nothing. No dark matter at all. Located 65 million light-years away, NGC 1052 is what's known as an ultra-diffuse galaxy. It's roughly the size of our Milky Way, but contains only about 1/200th of the number of stars, making it incredibly faint and transparent. Astronomers can literally see right through it. This transparency is what allowed them to make an incredibly precise measurement of its mass. By studying the motion of 10 bright star clusters within the galaxy, they could calculate how much gravity was needed to keep them orbiting at their observed speeds. The result was stunning. The motion of the star clusters could be accounted for entirely by the gravitational pull of the visible stars themselves. There was no need for, and no sign of, any additional mass from dark matter. This galaxy is a cosmic ghost ship sailing on the gravity of its stars alone. The immediate reaction within the scientific community was one of intense skepticism. Dark matter is not just a theory, it's a framework that explains so much of what we see in the universe. Finding a galaxy without it is like finding a forest without trees or an ocean without water. It directly contradicts the standard model of galaxy formation. The most logical conclusion was that there must be an error in the observations or the calculations. Perhaps the distance to the galaxy was wrong, throwing off the mass estimates, or maybe the star clusters were not true tracers of the galaxy's gravitational field. Follow-up observations, however, only strengthened the original finding. Not only was NGC 1052 real, but its dark matter deficiency was even more extreme than first thought. This discovery forces astronomers to confront a difficult and exciting question. How did this galaxy form? One compelling theory suggests a violent, high-speed collision might be responsible. Imagine two nascent galaxies in the early universe beginning to form within their protective halos of dark matter. If they were to merge in a specific, grazing collision, the dark matter and the visible matter could have been separated. The dark matter, which interacts only through gravity, could have sailed right on through the collision, continuing on its path. The visible gas and dust, however, would have collided, experiencing friction and shock waves that caused them to slow down and collapse into a new structure, a galaxy born from the wreckage but orphaned from its dark matter. This new galaxy, NGC 1052 would then have been left behind, a cluster of stars with nothing but their own faint gravity to hold them together. The existence of such an object is a double-edged sword for cosmology. On one hand, it appears to challenge the very necessity of dark matter. On the other, it provides some of the most compelling indirect evidence that dark matter is a real, physical substance that can be separated from normal matter, rather than just a modification of the laws of gravity. If dark matter were simply an illusion caused by our misunderstanding of gravity, then every galaxy should behave the same way under that same set of revised laws. The fact that this one galaxy behaves so differently shows that there is something extra, something particulate that the other galaxies have and this one does not. NGC 1052 is not a refutation of dark matter. It is a crucial piece of evidence that it is a tangible thing, an entity that can be present or absent, making its profound influence all the more undeniable. While magnetars like Swift-J 1845 push the boundaries of physics with their unimaginable magnetic forces, another type of cosmic signal has long perplexed astronomers with its sheer, raw power and breathtaking brevity. These are fast radio bursts, or FRB, intense blasts of radio energy that last for just milliseconds yet release as much power as our Sun emits over several decades. For years, most FRBs seemed to be one-off events, unpredictable and utterly random, making them nearly impossible to study in detail. That all changed with the discovery of a signal that didn't just repeat, but did so with the unwavering precision of a cosmic clock. This is FRB 180916, and its 16-day cycle of activity and silence is one of the most compelling puzzles in modern astronomy. Located in a spiral galaxy 500 million light-years away, this FRB isn't merely repeating, it operates on a strict schedule. For approximately 4 days, it will erupt, firing off multiple bursts per hour. Then, as if a switch is flipped, it falls completely silent for the next 12 days. After that, the cycle starts all over again. This perfect 16-day rhythm has been observed consistently, ruling out any chance of a coincidence. Such reliable periodicity points directly to a physical mechanism involving orbital motion. It's as if something is periodically swinging into a position that allows it to send these brilliant flashes of energy in our direction. The leading theory to explain this celestial metronome involves a binary system, a pair of objects locked in a gravitational dance. One of the most popular scenarios features a highly magnetized neutron star, like a magnetar, in orbit around a massive companion star. In this model, the magnetar is the engine of the burst, but as it travels along its elongated 16-day orbit, there is a point where it swings particularly close to its companion. During this close approach, the intense gravitational and magnetic interactions, or perhaps the dense wind from the massive star, could act as a trigger, unleashing the stored energy that results in the FRB. The 12 days of silence would correspond to the portion of its orbit where it's too far away for this triggering mechanism to work. Another possibility is that the repeating bursts are caused by a precession, or wobble, of the neutron star itself, slowly sweeping its emission beam across our line of sight like a lighthouse, with the 16-day period representing the full cycle of that wobble. What makes this regularity so profoundly important is that it provides a crucial clue to the environment surrounding the burst. A repeating cycle strongly suggests the FRB source is not being destroyed in the process, which rules out some of the more cataclysmic one-time event theories. Furthermore, the 16-day period helps astronomers estimate the size of the system. The orbital mechanics imply that the two objects are likely separated by a distance comparable to the distance between Earth and Mars, giving us a tangible scale for this incredibly energetic phenomenon. This single patterned signal has done more to advance the study of FRBs than perhaps any other discovery, transforming them from total mysteries into physical events that we can begin to dissect and understand. It offers a rare, predictable window into one of the universe's most extreme and enigmatic processes. While the rhythmic pulse of a distant fast radio burst offers a predictable mystery, other discoveries unfold over much longer timescales, requiring immense patience to even glimpse. The hunt for moons beyond our solar system is one of astronomy's most daunting challenges. For decades, as the catalogue of confirmed exoplanets swelled into the thousands, the list of exomoons remained stubbornly empty. The technical difficulty of spotting a moon orbiting a planet that itself is just a speck of light flickering around a distant star is almost incomprehensible. That's why the potential discovery of Kepler 1708b is so electrifying. This candidate, a moon possibly the size of Neptune orbiting a Jupiter-sized world 5,500 light-years away, isn't just a new object. It's a triumph of ingenuity and a window into an entirely new class of celestial bodies. The method used to detect it is a testament to how clever astronomers have become. They employed a technique known as transit photometry, the same workhorse method that has identified the majority of known exoplanets. It involves staring at stars and meticulously measuring their brightness. When a planet passes in front of its host star, it causes a predictable, symmetrical dip in the light curve. Finding an exomoon requires looking for tiny fingerprints left in the data around that main planetary dip. A large enough moon could cause its own additional, smaller dip in starlight either just before or just after the planet transits. Even more subtly, the moon's gravity can tug on the planet, causing the exact timing of the planet's transit to wobble slightly from orbit to orbit. It was by scouring the data from NASA, a Kepler space mission, for these incredibly faint signatures that researchers identified the tantalizing hints of Kepler 1708b. The data paints a picture of a truly gargantuan world. The candidate moon appears to be about 2.6 times the size of Earth, making it significantly larger than any moon in our own solar system. To have a moon of that scale orbiting a planet 10 times more massive than Jupiter challenges our terrestrial perspectives. In our neck of the woods, moons are generally much smaller than their parent planets. This discovery suggests that what we consider normal in our solar system might be the exception rather than the rule. We may live in a universe where giant planets routinely capture or form with giant moons, creating binary planetary systems that blur the line between a planet-moon pair and a double planet system. Confirming this discovery, however, is the real hurdle. The signals are so incredibly faint that they linger right at the very edge of what our current telescopes can detect. They are whispers in a hurricane of data noise. Other phenomena can masquerade as an exomoon signal. A faint second planet in the system could create similar transit timing variations, or star spots on the host star's surface could create dips in brightness that mimic a moon's transit. The scientific process demands rigor, and right now, Kepler 1708b remains a compelling candidate, not a confirmed discovery. Future observations by the James Webb Space Telescope may provide the critical evidence needed to push this finding from probable to proven. By analyzing the atmosphere of the planet during transit, JWST could potentially even detect the atmospheric signature of the moon itself if it exists, finally settling the debate. Beyond the technical achievement, the existence of such giant exomoons has profound implications for the search for life. Our solar system has taught us that moons can be worlds of astounding geological activity and potential habitability, often far more so than the planets they orbit. Jupiter's moon Europa and Saturn's moon Enceladus, both icy worlds with vast subsurface oceans, are considered among the most promising places to look for life beyond Earth. A gas giant planet itself may be inhospitable, but if it resides in its star's habitable zone, the region where temperatures are right for liquid water, then any large, rocky moon orbiting it could be a prime candidate for habitability. A world like Kepler 1708b, if it is real, would likely be a gas giant itself, not a rocky moon. But its discovery validates the methods and proves that large exomoons can and do exist. It opens the door to the possibility that somewhere out there, a rocky moon with twice the mass of Earth is orbiting a stable gas giant, warmed by its star, with an atmosphere and perhaps even oceans, a perfect sanctuary for life, hidden in the shadow of a giant. Yet as we hunt for moons that could harbor life, we are reminded that some of the most fascinating worlds have no star to call home at all, wandering the cold, dark voids of interstellar space. One such loner, a rogue planet known as SIMP J0 1365663+0933473, challenges the very definition of what a planet can be. This object, with a mass just over a dozen times that of Jupiter, was discovered drifting alone about 20 light-years away from us. It is not orbiting any star. It is a true cosmic orphan, cast out from its native system to travel the galaxy solo. In the eternal night of deep space, you would expect such a world to be a frozen, dead, and inert ball of gas. But SIMP is anything but inert. It is a raging powerhouse possessing a magnetic field so incredibly potent that it creates brilliant, planet-sized auroras that light up the darkness all on its own. This is a phenomenon that, until now, we believed required a star. On Earth, our beautiful northern and southern lights are the result of charged particles from the Sun being channeled down into our atmosphere by our planet's magnetic field. SIMP has no sun, there is no stellar wind constantly battering it, and yet its magnetic field is about 200 times stronger than Jupiter's, itself a planet famous for its powerful magnetosphere. This immense field is generating auroras through a completely different and far more mysterious process. The leading theory suggests that the planet's own atmosphere might be fueling the light show. As SIMP travels through space, its strong gravity could potentially pull in trace amounts of hydrogen and other particles from the interstellar medium. Alternatively, a volcanic moon, if it has one, could be spewing material into space that then becomes ionized and caught in the magnetic trap. But the most intriguing possibility is that the planet's interior dynamics are so intense that they are generating currents powerful enough to produce the auroras entirely from within, a self-sustaining celestial generator operating in profound isolation. This incredible activity places SIMP squarely on the blurry boundary that separates giant planets from failed stars known as brown dwarfs. Brown dwarfs are objects too massive to be called planets, but not quite massive enough to ignite sustained hydrogen fusion in their cores and become true stars. They often form like stars from the collapse of a gas cloud, and many of them are known to have strong magnetic fields and auroral activity. SIMP, however, is believed to have formed like a planet around a star before being violently ejected. Its existence forces us to ask a fundamental question. Is the primary difference between a planet and a brown dwarf simply how it formed, or is it the physics occurring inside it? SIMP behaves like a brown dwarf with a complex and active magnetic personality, but it has the mass and likely the origin story of a planet. It is a hybrid object, a planetary mass body with stellar-level ferocity, demonstrating that the cosmic classification system is far messier and more fascinating than our neat textbook categories would suggest. Studying loners like SIMP provides an unparalleled opportunity to understand the inner workings of gas giants without the complicating glare of a parent star. In a normal solar system, the intense light from a star makes it incredibly difficult to study the faint, intrinsic properties of its planets. A rogue planet floating in the dark is a clean slate. By analyzing the radio waves and subtle light emissions from its auroras, astronomers can peer into its interior, mapping the dynamics of its metallic hydrogen core and understanding how such a powerful magnetic dynamo is generated and maintained. This knowledge doesn't just apply to orphans, it helps us understand the magnetic hearts of gas giants everywhere, including those in our own solar system. SIMP teaches us that a planet doesn't need a star to be a dynamic, complex, and brilliantly active world. It can create its own light, its own weather, and its own spectacular phenomena, a self-contained universe adrift in the endless night. But the true chaos of GW Orionis isn't just its 3 stars. It's the colossal disk of gas and dust swirling around them, a birthplace for planets that has been utterly warped and torn apart by their gravitational dance. This isn't a flat, orderly dinner plate like the one that once surrounded our young sun. This protoplanetary disk is a twisted, disjointed mess with an inner ring that is dramatically misaligned, tilted by a jaw dropping 38 degrees relative to the outer disk and the orbital plane of the central stars. It looks less like a celestial construction site and more like a broken hula hoop spinning wildly around a trio of fiery dancers. This profound misalignment is a direct and violent product of the 3-body problem, a gravitational puzzle that is famously impossible to solve with perfect predictability. The 3 stars don't orbit in a neat, flat plane. their paths are dynamic and constantly changing. As they tug on each other, they also exert immense and conflicting gravitational pulls on every particle in the surrounding disk. Think of it like a game of cosmic tug-of-war where the ropes are being yanked in 3 different directions at once. This doesn't just tilt the disk, it torques it, warping its structure and creating immense friction within the dust and gas itself. Observations from the Atacama Large Millimeter Array revealed that this gravitational chaos has likely shredded the disk, causing it to break into distinct, precessing rings that are all orbiting at different angles. It is within this torn and turbulent ring, this sliver of a shattered disk, that astronomers found the first direct evidence of a planet forming, a world being born into a system of pure pandemonium. The existence of this planet is what truly throws our textbooks into disarray. Our core model of planet formation, developed by studying sedate, single-star systems like our own, is based on the idea of a calm, coherent disk. In that model, dust particles gently collide and stick together, slowly building up into planetesimals and eventually planets, all orbiting neatly in the same plane as the star's equator. GW Orionis shatters that peaceful picture. It proves that planets can form under conditions of extreme gravitational stress within disks that are anything but calm. This forces a complete re-evaluation of the resilience of the planet-forming process. It suggests that what we once considered ideal conditions might just be one way to build a world, and that planetary systems can emerge from what looks like pure cosmic chaos. The implications for the potential planets in this system are mind-bending. A world forming in that misaligned ring would have a sky unlike any other. Its suns would rise and set in a wildly complex pattern, sometimes appearing in different parts of the sky for weeks on end. The concept of a stable, circular orbit within the habitable zone becomes almost meaningless when the very definition of orbital plane is fractured. This discovery opens up a vast new parameter space for exotic planetary systems, suggesting that many worlds could be born into wildly tilted orbits, perhaps even orbiting perpendicular to their star's rotation. GW Orionis is more than just a curiosity. It is a stark lesson in cosmic diversity, showing us that the process of creation is far messier, more violent, and infinitely more creative than we ever imagined. Just when the case for dark matter-deficient galaxies seemed to be settling, the cosmic courtroom was thrown back into session with a new and even more contentious piece of evidence. Enter AGC 114905, an ultra-diffuse galaxy that reignited the debate and proved that in science, no discovery is ever truly final. This seemingly innocuous smudge of light became the center of a fierce cosmological argument, a debate that strikes at the very heart of how we measure the universe and what we believe it's made of. The initial findings, published in 2021, were bold and unequivocal. After 40 hours of meticulous observation using the Very Large Array Radio Telescope, a team of astronomers reported that the motion of hydrogen gas within AGC 114905 showed no discernible sign of a dark matter halo. According to their measurements, the rotation of the gas could be perfectly explained by the gravity of the visible matter alone. This was a potentially monumental confirmation that NGC 1052 DF2 was not a fluke but part of a new class of galaxy. The researchers were so confident that they proposed the dark matter thought to be inherent to all galaxies must have been somehow stripped away, perhaps by interactions with neighboring galaxies in the distant past. But the scientific process is built on skepticism and verification. Other teams quickly scrutinized the data, and a very different story began to emerge. The central critique came down to one of the most fundamental and tricky aspects of astronomy, the angle of inclination. When we observe a distant galaxy, we're seeing it from a specific fixed perspective. To accurately calculate its mass and the true speed of its rotating gas, we must know its tilt relative to our line of sight. A galaxy that is facing us nearly head-on will appear to rotate much more slowly than one we are seeing edge-on, even if their intrinsic rotational speeds are identical. The original study had estimated the inclination of AGC 14905 to be about 32 degrees, meaning it was somewhat tilted away from a face-on view. The opposing argument, backed by new analyzers and simulations, suggested this was a critical miscalculation. They proposed that the galaxy is actually much closer to being face-on than previously thought. If that were true, its apparent slow rotation wouldn't be due to a lack of dark matter at all, but simply a geometric illusion. The actual rotational velocity, if we could see it from the correct angle, would be much faster, requiring the gravitational pull of a massive, unseen dark matter halo to hold it together. This isn't just a minor quibble over numbers, it's a fundamental reassessment of the object's basic geometry that completely changes the interpretation of the data. This back and forth is not a sign of failure in astronomy, but rather a brilliant display of the scientific method in action. It highlights the immense challenges of doing forensic science across millions of light years. We cannot travel to these galaxies to get a better look. We must rely on interpreting the faint whispers of light and radio waves that reach us, and sometimes those whispers can be ambiguous. The controversy around AGC 14905 forces cosmologists to refine their tools and question their assumptions more rigorously than ever before. It has spurred the development of more sophisticated methods for estimating galactic inclinations and modeling the complex dynamics of diffuse gas. Ultimately, the impact of this ongoing debate extends far beyond the fate of one single galaxy. It tests the resilience of the entire dark matter paradigm. If such galaxies are conclusively proven to exist, it means our models of galaxy formation are incomplete and need to account for how a galaxy can form or evolve without this invisible anchor. If, however, they are all eventually explained away as measurement errors, it would powerfully reinforce the idea that dark matter is not just a convenient theory but an indispensable component of the cosmos, a universal glue that is absolutely essential for building the structures we see. For now, AGC 14905 remains a tantalizing mystery, a cosmic Rorschach test where different scientists see different truths, each interpretation pushing our understanding of the universe's hidden architecture to its very limits. While the controversy around dark matter-deficient galaxies forces us to question the universe's hidden scaffolding, other cosmic systems reveal a more blatant and far more violent form of consumption. If a galaxy missing dark matter is a silent anomaly, then a black widow pulsar is a screaming predator. These are not simply binary star systems, they are cosmic murder scenes playing out in slow motion, where one partner is methodically devouring the other. The name is chillingly apt, drawn from the spider species where the female consumes the male after mating. In the depths of space, a rapidly spinning neutron star is playing the role of the Black Widow, and its stellar companion is on the menu. The story of a Black Widow system begins with a relatively normal binary pair. Two stars are born together and orbit one another for millions of years. Eventually, the more massive of the two exhausts its fuel and explodes in a supernova. If the conditions are right, the remnant core collapses into a city-sized neutron star, an object so dense it packs more mass than our Sun into a sphere just a few miles across. This newborn pulsar is a cosmic powerhouse, spinning hundreds of times per second and blasting out twin beams of intense radiation from its magnetic poles. Like a catastrophic lighthouse, these beams sweep across the sky, and if one happens to point toward Earth, we detect it as a perfectly regular radio pulse. This is how we first discover these objects as rhythmic, precise ticks in the data from radio telescopes, but the real horror begins after the explosion. The supernova can sometimes kick the system, bringing the pulsar and its companion star into a much tighter, more intimate orbit. Now, separated by a distance often smaller than that between the Sun and Mercury, the companion star is utterly at the mercy of the pulsar's immense gravity. This is where the consumption starts. The pulsar uses its gravitational pull to strip away the outer layers of its partner, drawing a stream of gas onto itself. This process, known as accretion, fuels the pulsar even further, causing it to spin faster and become even more energetic. It's a vicious, self-sustaining cycle. The more the pulsar feeds, the stronger it becomes, and the more efficiently it can continue to feed. The victim star isn't just being quietly siphoned, it's being bombarded. The pulsar doesn't just emit lighthouse beams, it also unleashes a relentless torrent of high-energy particles and radiation, a stellar wind of unimaginable ferocity. This wind strikes the companion star with the force of a constant hurricane, heating its surface to tens of thousands of degrees and actively blasting the stolen material away into space. In many cases, this pulsar wind is so powerful that it begins to ablate the companion, eroding it away like a sandbank in a relentless tide. Astronomers can actually detect the hazy cloud of ionized gas being blown off the star, a telltale shroud of death that surrounds the entire system. Over hundreds of millions of years, this process continues inexorably. The companion star, once a sun-like object, is whittled down to a fraction of its original mass. Many black widow pulsars have companions that have been reduced to the mass of a large planet, a mere cinder of their former selves. Eventually, the pulsar may completely evaporate its partner, leaving behind a lone neutron star with the ghost of a meal lingering in its orbit. The discovery of these systems is a triumph of multi-wavelength astronomy. We first find the radio pulses, but the true nature of the crime is revealed by observing the optical light from the beleaguered companion. Its brightness will vary dramatically as it is tidally locked, with one hemisphere perpetually facing the blazing pulsar and being roasted, creating a stark contrast between a blistering day side and a comparatively cooler night side. Studying these cosmic predators is about more than just witnessing celestial violence. Black widow pulsars are extreme natural laboratories. They allow us to study the behavior of matter under the most intense gravitational and magnetic fields possible, conditions we could never hope to recreate on Earth. They teach us about the end stages of binary star evolution and the ultimate fate of systems that survive the trauma of a supernova. Each ticking pulse is a countdown to a stellar demise, a grim reminder that even among the stars there can be predators and prey, locked in a fatal dance that ends with only one survivor. But if the predatory dance of a black widow pulsar represents a slow, methodical consumption, the next discovery points to a void of a different kind, an immense, chilling emptiness that may be the largest single structure humans have ever identified. As we map the faint afterglow of the Big Bang itself, the cosmic microwave background, we find it is not perfectly uniform. It is dotted with tiny fluctuations in temperature, the seeds from which all galaxies and clusters would eventually grow. Yet one feature stands out not for its heat but for its profound cold. This is the Great Cold Spot, a region of space so vast and so inexplicably chilly that it has sparked some of the most daring theories in all of modern cosmology. Stretching nearly 2 billion light-years across, the Great Cold Spot is a colossal anomaly in the CMB, the universe's baby picture. In this ancient light, it appears as a significant dip in temperature, a place that is about 70 microkelvin colder than its surroundings. While that might sound trivial in the context of the incredibly smooth CMB, it is a staggering deviation. For years, the most accepted explanation was that this cold spot was not a feature of the primordial universe, but a shadow cast by a latter-day structure, a cosmic supervoid. The theory was elegant in its simplicity. If light has to expend energy climbing out of an enormous gravitational well, a region of space with far less matter than average, it loses energy and redshifts, making the CMB light coming from that direction appear colder to us. Astronomers scoured the suspected region, and indeed they found a large supervoid, now known as the Eridanus supervoid, which seemed to align with the cold spot's location. Case closed, it seemed. However, the plot quickly thickened. Upon closer inspection, the numbers simply didn't add up. The Eridanus supervoid, while enormous, is not nearly large enough or empty enough to account for the profound temperature drop observed in the Great Cold Spot. The physics of the integrated Sachs-Wolf effect, which describes this cooling, dictated that the void would need to be far more extreme to create such a signature. It was like finding a small hill and trying to claim it was responsible for casting a shadow hundreds of miles long. The discrepancy was too great to ignore, forcing cosmologists to confront an unnerving possibility. What if the cold spot is not an illusion caused by a later structure, but a genuine feature imprinted on the universe at the moment of its birth? This is where the theories become truly spectacular. If the cold spot is primordial, it challenges the standard model of cosmology, which struggles to explain how such a massive fluctuation could have been generated during inflation, the universe's rapid initial expansion. One of the most mind-bending proposals is that the Great Cold Spot is nothing less than a bruise, a cosmic scar left from a collision with another universe. In the multiverse theory, our universe is just one bubble in a vast froth of countless other bubble universes, each with its own distinct physical laws. If, during the inflationary period, our budding universe bumped into a neighboring bubble, the energy released at the boundary of that collision could have left an imprint on the CMB, an imprint of cold that we now observe as the Great Cold Spot. The implications of this are, of course, staggering. It would be the first tangible, observational evidence for the existence of a multiverse, a concept that has until now been purely theoretical. It would mean our universe is not alone and that we have physical proof of a reality beyond our own cosmic horizon. Critics of this idea rightly point out its extraordinary nature, arguing that more conventional, if still unknown, physics within our single universe could be at play. Perhaps it is evidence of a giant magnetic field from the early universe, or a texture, a flaw in the fabric of space-time itself left over from a phase transition in the primordial cosmos. The Great Cold Spot remains one of the most persistent and profound mysteries in all of science precisely because it refuses to yield a simple answer. It sits at the intersection of what we can observe and what we can only dream of, a Rorschach test on the sky where some see a fascinating large-scale structure and others see the fingerprint of another reality. Its continued study pushes our telescopes and our theories to their absolute limits, a chilling reminder that the deepest secrets of the cosmos are written not in the brilliant light of stars, but in the faint, cold whispers of the void. While the Great Cold Spot hints at collisions on the grandest of scales, our own galaxy is the stage for a different kind of violent ejection, one that sends individual stars screaming into the void at unimaginable speeds. These are the hypervelocity stars, stellar projectiles rocketing through the Milky Way at speeds exceeding 1 million miles per hour, so fast that they are on a one-way trip to escape the galaxy's gravitational grasp entirely. They are the cosmic equivalent of a bullet fired from a gun, and their origins are as dramatic as their journeys. The story of how a star gets up to such incredible velocity is a tale of gravitational slingshots and cosmic cataclysms. There are two primary engines capable of launching a star into interstellar space at these extreme speeds. The first involves the supermassive black hole at the very heart of our galaxy, Sagittarius, a star. When a binary star system, two stars orbiting each other, wanders too close to this gravitational monster, a violent dance ensues. The black hole's immense tidal forces can tear the binary pair apart. One star gets captured into a tight orbit around the black hole, while the other is flung away at a tremendous fraction of the speed of light, like a stone from a sling. This three-body interaction is one of the most efficient accelerators in the universe. The second method involves the immense power of a supernova explosion in a tight binary system. When one star in a pair goes supernova, it can suddenly lose a significant portion of its mass. The gravitational bond holding the two stars together is instantly weakened, and the surviving companion can be flung off on a new, high-speed trajectory, released from its orbit like a swung ball whose string has been cut. In some extreme cases, if the supernova is slightly off-center or asymmetric, the neutron star or black hole remnant itself can receive a powerful kick, becoming a runaway stellar corpse racing through the galaxy. Detecting these stellar speedsters is a painstaking process that relies on measuring two key properties: their radial velocity and their proper motion. Astronomers use the Doppler shift in a star's light to determine how fast it is moving directly toward or away from us. They then combine this with incredibly precise measurements of the star's actual movement across the sky over many years to calculate its true, three-dimensional velocity through space. When that number is far higher than the average orbital speed of stars in the galaxy, they know they've found something extraordinary. The first hypervelocity star was discovered in 2005, a massive blue star traveling at over 1.5 million miles per hour, and many others have been found since, each with its own unique trajectory pointing back to a moment of immense violence. But these stars are more than just celestial curiosities. They are powerful tools for galactic cartography. A hypervelocity star is essentially a tracer bullet fired from a known location. By tracing its path backwards across the sky, astronomers can often pinpoint its precise origin. Those that can be tracked back to the galactic center provide incredibly strong supporting evidence for the presence and mass of our central supermassive black hole, confirming the theories about the extreme environment there. Others, whose paths originate in the galactic disk, help us map the distribution of mass throughout the Milky Way, including the elusive dark matter halo. Their trajectories are influenced by the gravity of everything they pass, making them natural probes of the unseen structure of our galaxy. The existence of these stars also has fascinating implications for the intergalactic medium. A hypervelocity star that successfully escapes the Milky Way will spend eternity traveling through the lonely void between galaxies. Any planets that manage to survive the ejection process would be orbiting a star hurtling through perpetual night, far from the nurturing light of any galactic center. It's a bleak vision of cosmic isolation, yet it also suggests that stars and any potential life they might carry could possibly travel between galaxies, seeding the vast cosmos in a way we never before considered. Each hypervelocity star is a testament to the violent forces that shape our galaxy, a silent witness to eruptions of unimaginable power now on an endless journey through the dark. While the hypervelocity stars represent the aftermath of galactic violence, propelling suns on one-way trips into the void, we now look back to the very dawn of time to a galaxy that shouldn't exist at all. Meet HD1, a smudge of light that has sent shockwaves through the world of cosmology. This isn't just an old galaxy, it is the most distant and therefore the earliest galaxy ever confirmed at the time of its discovery. We are seeing it as it was a mere 330 million years after the Big Bang, a time when the universe was still a murky, opaque soup of cooling particles barely out of its infancy. In this primordial darkness, conventional wisdom says the first galaxies should be tiny, fragile things, slowly sputtering to life as they pull in their first wisps of gas. HD1 is the complete opposite. It is a cosmic behemoth, a raging furnace of star formation that is breaking all the rules and forcing a complete rewrite of our models for the universe's childhood. The sheer intensity of HD1 is what makes it so utterly baffling. Observations indicate it is forming new stars at a mind-shattering rate, potentially over 100 stars every single year. To put that into perspective, our own Milky Way galaxy, which is vastly larger and more mature, manages to form maybe 1 or 2 new stars per year. HD1 is producing 100 times more stars in an epoch when it should barely be able to produce any. It's like finding a toddler who can lift a car over their head. The laws of physics, as we understand them, simply don't allow for it. This incredible rate of star formation presents a monumental puzzle. Where did it get all the raw material, the gas, to form so many stars so quickly? How did it assemble itself with such breathtaking speed in a universe that was still so young? Our best simulations of early galaxy formation cannot produce something like HD1. It is an outlier that points to a fundamental gap in our knowledge, suggesting that the seeds of the first galaxies were planted much earlier and grew much faster than anyone ever thought possible. This impossible activity has led astronomers to propose two equally extraordinary explanations for what might be powering HD1. The first, and perhaps most tantalizing, possibility is that we are witnessing the first generation of stars in the entire cosmos. These hypothetical objects, known as population 3 stars, are the holy grail of stellar astronomy. They are thought to be monstrously large, pure behemoths composed only of hydrogen and helium, the primordial elements forged in the Big Bang. Without any heavier elements to help them cool and fragment, the clouds that formed these stars would have collapsed into giants hundreds of times more massive than our Sun. These stars would have lived fast and died young, burning at ferocious temperatures and ending their short lives in cataclysmic supernova that would have seeded the universe with the first heavy elements. The light from population 3 stars would be unlike anything we see today, overwhelmingly bright in ultraviolet light. The observed properties of HD1 match this signature perfectly, suggesting we may be getting our first ever glimpse of these mythical cosmic pioneers. The second, more violent theory is that we are not looking at a frenzy of star birth at all, but at the voracious appetite of a supermassive black hole. At the galaxy's core, there could be an accretion disk of material swirling around a black hole so massive that its mere existence so early in the universe is its own profound mystery. As vast amounts of gas are pulled into this gravitational whirlpool, it would be heated to millions of degrees, blasting out enormous amounts of high-energy ultraviolet radiation, the same kind of light we see coming from HD1. If this is the case, then the black hole would have to be colossal, weighing in at over 100 million times the mass of our Sun. The problem is, we have no clear idea how a black hole could grow to such an immense size in such a tiny fraction of the universe's lifetime. It would have to start from a seed far larger than any supernova remnant could provide, pointing to exotic formation mechanisms that we are only beginning to theorize about. Whether it's powered by the first stars or the most ancient of black holes, HD1 stands as a monumental challenge. It pushes the James Webb Space Telescope to its absolute limits, forcing us to stare back to the very edge of what is observable. This galaxy is a direct message from the infancy of creation, telling us that the universe got off to a much more dynamic and explosive start than our textbooks ever allowed for. It suggests that the dark ages of the cosmos, that period before the first lights switched on, was far shorter and far more eventful than we dreamed. While the hunt for distant giants like Planet 9 captures the imagination, some of the most revealing discoveries are made by patiently studying the smaller, dimmer objects that litter the outer darkness. One such world, initially known only by the catalog designation 2014 UZ224, earned the far more charming nickname DD. For years, this was just a faint speck of light detected by the groundbreaking Dark Energy Survey in Chile, a tiny blip whose true nature was completely unknown. Was it a small, nearby asteroid or something much larger and far more distant? The initial observations could only tell us that it was there, a ghost in the vast machine of the outer solar system, its secrets locked away by immense distance and profound darkness. The key to unlocking DD's mystery lay in a powerful synergy between two observatories. The first was the iconic Atacama Large Millimeter Array, or OLMA, a collection of 66 radio telescopes high in the Chilean desert that works together to act as a single, massive eye on the universe. ALMA has the unique ability to detect the faint heat signature of cold objects. While DD reflects virtually no sunlight, it still emits a tiny amount of thermal radiation, a faint whisper of warmth left over from its formation billions of years ago. By tuning into this radio wavelength emission, the ALMA team could finally measure how much heat DD was giving off. This thermal measurement was the critical piece of the puzzle. By combining it with optical data that provided the object's distance and reflectivity, astronomers could perform a remarkable calculation. They determined that DD is roughly 635 kilometers in diameter, making it about 2/3 the size of the dwarf planet Ceres in the asteroid belt. This confirmed its status as a bona fide dwarf planet, a substantial world in its own right. This discovery transformed our understanding of DD from a mere pinprick of light into a tangible, physical place. It is a resident of the Kuiper belt, that vast disk of icy debris that stretches beyond the orbit of Neptune. DD's orbit is incredibly elongated, taking it more than 92 times farther from the Sun than Earth is at its most distant point. At that range, sunlight is vanishingly faint. A day on DD would be darker than a moonlit night on Earth and unimaginably cold. The fact that such a sizable object remained undetected for so long is a testament to the incredible darkness of the solar system's frontier, and suggests that many more worlds of similar size are likely lurking out there, waiting to be found. But DD is more than just a record holder for distance. It is a potential messenger, its path through space possibly shaped by forces we have yet to directly observe. The orbits of many distant objects, including DD, exhibit slight gravitational tweaks and Chinese letter, or clustering that some scientists argue could be the work of a massive, undiscovered planet. This hypothetical world, often called Planet 9, would be several times more massive than Earth and orbit on a highly inclined path far beyond Pluto. The presence of such a planet would gravitationally shepherd objects like DD into similar, tilted orbits. While DD's orbit alone isn't proof of Planet 9, it adds one more day to point to a growing celestial conspiracy. Each newly discovered distant object with a strange orbit is another clue, another piece of evidence that our solar system's story may not be fully written. DD, a cold, dark world on the very edge of our vision, might ultimately be one of the guides that leads us to the discovery of a true solar system giant, forever changing the map of our own cosmic backyard. And if you thought the triple-star chaos of GW Orionis was complex, prepare to meet a world that feels like it was pulled straight from science fiction. This is KOI-5ab, a real-life Tatooine that takes the concept of a multiple-star system to its absolute extreme. Discovered by NASA Kepler mission over a decade ago, this gas giant was initially just another blip in the data, one of thousands of candidate planets. But as astronomers took a closer look, they realized they had found something truly special. KOI-5ab doesn't just orbit a single star, it is part of an intricate triple-star system, a gravitational ballet where the planet is vastly outnumbered by its suns. The arrangement of this system is a masterpiece of celestial architecture. The primary star, KOI-5a, is the planet's host. It's a fairly normal star, similar to our Sun, and it forms a relatively tight binary pair with another star, KOI-5b. These two stars whirl around each other about every 30 years, locked in a close embrace. The planet KOI-5ab orbits just this primary star, KOI-5a, on a wildly tilted and misaligned path. But the dance doesn't end there. Circling this inner pair from a much greater distance is a third star, KOI-5c, which takes about 400 years to complete a single orbit around the central binary. From the surface of this hypothetical world, the sky would be a constantly shifting spectacle. One sun would dominate the sky, while the other two would appear as incredibly brilliant stars, sometimes close together, sometimes far apart, casting multiple, shifting shadows in an eternal, complex day. The very existence of KY5ab is a minor miracle of gravitational survival. In the early, chaotic days of a multi-star system, the competing gravitational pulls from multiple stars can easily disrupt the gentle process of planet formation. Protoplanetary disks can be torn apart, and any fledgling planetary cores can be violently ejected from the system entirely. For a planet to form and maintain a stable orbit in such a turbulent environment, it must either form very close to its host star where that star's gravity is overwhelmingly dominant, or it must somehow migrate into a stable orbital resonance, a gravitational sweet spot where the tugs from the other stars cancel each other out over time. KY5ab seems to have taken the first path, orbiting its primary star, KOI-5a, at a distance closer than Mercury orbits our Sun. At that range, the gravitational bond is strong enough to shield it from the most disruptive influences of its stellar siblings. However, that protection isn't perfect, and the other stars have still left their mark. The planet's orbit is severely misaligned with the equatorial plane of its host star. This suggests that at some point in the system's history, the gravitational influence of the second star, KOI-5b, likely gave the planet a significant gravitational kick, knocking it off its original, presumably flat orbital course. This event could have occurred during the planet's migration or even after it had formed, a lasting scar from a moment of cosmic violence. The system serves as a stunning natural laboratory for studying how planets can persist in some of the most gravitationally hostile environments imaginable, proving that planet formation is a resilient and adaptable process, capable of finding a way even when the odds are stacked against it. Yet, even as we find planets in the most chaotic of systems, a star much closer to home staged a dramatic and mysterious performance that captivated the entire world. In late 2019, the constellation Orion, one of the most recognizable patterns in the night sky, began to look wrong. Its familiar form was altered. Betelgeuse, the brilliant red supergiant that marks the hunter's shoulder, was fading, not subtly but dramatically. Over a matter of months, this beacon of the winter sky dimmed to a mere shadow of its former self, losing nearly 2/3 of its brightness and plunging from the 9th to the 21st brightest star in the sky. For astronomers and the public alike, it was a breathtaking event. The most immediate and thrilling question on everyone's mind was simple: was this it? Was Betelgeuse about to go supernova? The possibility was not without merit. Betelgeuse is a ticking time bomb. It is a colossal star, so vast that if it were placed at the center of our solar system, its surface would extend beyond the orbit of Mars, engulfing Earth and all the inner planets. It has burned through its nuclear fuel at a ferocious rate and is now in the final act of its life, destined to end in a cataclysmic Type II supernova explosion. When that happens, it will be a spectacular sight visible even in broad daylight for weeks. The great dimming event seemed like it could be the final curtain call. But the universe is a master of misdirection, and the truth behind the dimming turned out to be far more complex and fascinating than a simple countdown to doom. As the world's most powerful telescopes turned their gaze toward the ailing star, a collaborative detective effort began to unravel the mystery. The key data came from the European Southern Observatory's Very Large Telescope, which had captured an incredibly detailed image of Betelgeuse's surface just before the Great Dimming. When compared with images taken during the event, the cause became startlingly clear. The star hadn't dimmed uniformly. Instead, a huge, dark patch had appeared on its southeastern face. The dimming wasn't a sign of the star's internal engine failing. It was a celestial veil, a shadow cast across its brilliance. But what could possibly cast a shadow that large on a star so enormous? Two compelling theories emerged, and the answer likely involves a bit of both. The first points to the star's own turbulent nature. Betelgeuse is a seething cauldron of convection. Massive cells of plasma, larger than our entire sun, constantly bubble up from the interior, heat the surface, and then sink back down. astronomers proposed that a particularly massive convective cell could have welled up and then cooled dramatically as it reached the star's surface, creating a temporary, cool, dark spot of a scale we had never witnessed before. This alone could account for a significant portion of the dimming. However, the second act of this drama involved the star's prodigious mass loss. Red supergiants like Betelgeuse are constantly shedding their outer layers into space, creating their own personal nebula of ejected gas and dust. The leading theory holds that a recent, large ejection of material from the star's surface drifted outward. Then, when a subsequent convective event sent a wave of cooler gas upward, the temperature dropped just enough at the precise moment for the ejected material to condense into solid dust grains right in front of our line of sight. This sudden formation of a vast, localized dust cloud acted like a cosmic parasol, blocking a huge portion of the star's light from reaching Earth. It was a perfect storm of stellar activity, a cold spot on the star providing the seed for a dust cloud that then amplified the dimming effect far beyond what the cold spot could achieve alone. By April 2020, Betelgeuse had returned to its normal brightness, its dramatic performance over. The event provided an unprecedented learning opportunity. It gave us a front-row seat to the violent and complex processes that govern the final stages of a massive star's life. We learned that such extreme dimming events are part of Betelgeuse's natural cycle, a symptom of its immense instability rather than a specific herald of its death. While its supernova is inevitable, it could still be 100,000 years away. The Great Dimming was not a final gasp, but a powerful reminder of the dynamic and ever-changing nature of the cosmos, a preview of the incredible physics that will one day culminate in one of the most spectacular events our galaxy will ever witness. And it was this very trait that catapulted a small, faint object from a mere curiosity into one of the most heated debates in modern astronomy. The object was Oumuamua, the first confirmed visitor from another star system, and its behavior challenged everything we thought we knew about the simple physics of celestial motion. After it slingshotted around the Sun, something extraordinary happened. Instead of continuing on a path dictated solely by gravity, as every comet and asteroid we've ever observed should, Oumuamua experienced an additional, small but undeniable push. It was accelerating ever so slightly away from the Sun. This non-gravitational acceleration was the catalyst for a firestorm of scientific inquiry and public fascination, a mystery that remains unsolved to this day. The immediate and most scientifically conservative explanation pointed to a natural phenomenon common in our own solar system, outgassing. When a comet approaches the Sun, its icy surface heats up, turning frozen solids directly into gas in a process called sublimation. This jetting gas acts like a natural thruster, imparting a gentle push that can alter the comet's trajectory. The problem with this theory for Oumuamua was the complete and utter lack of any visible coma or tail, the telltale cloud of gas and dust that surrounds an active comet. Our most powerful telescopes scanned it intently and found nothing. No gas, no dust, no water vapor. It was behaving like a rocket without any visible exhaust, a seeming violation of Newton's third law. Proponents of the outgassing theory argued that perhaps Oumuamua was made of very pure hydrogen ice or other exotic ices that would sublimate without leaving a dusty trail, or that its dust particles were unusually large and heavy, failing to brighten enough for us to see. These are plausible ideas, but they remain entirely speculative without a shred of direct evidence. This absence of a clear, natural explanation opened the door for more speculative and far more exciting possibilities. The most famous of these was put forward by astronomer Avi Loeb, who suggested we must at least consider the possibility that Oumuamua was not a natural object, but a piece of advanced alien technology. His hypothesis focused on the object's strange, flattened shape, potentially like a pancake or a cigar, and the fact that the acceleration was smooth and continuous, not erratic like you might expect from uneven outgassing. He proposed it could be a light sail, a vast, thin sheet designed to be pushed by the radiation pressure from stars. A derelict solar sail from a distant civilization could, in theory, account for the precise way it accelerated. While this idea captured the global imagination, the vast majority of the scientific community remains deeply skeptical, arguing that an extraordinary claim requires extraordinary evidence and that we should exhaust every possible natural explanation before leaping to an extraterrestrial one. Other theories have since emerged, each attempting to solve the puzzle without invoking little green men. One of the most compelling new natural explanations involves molecular hydrogen. The theory suggests that Oumuamua could have been a hydrogen iceberg, formed in the cold, dense core of a giant molecular cloud. As it journeyed into our inner solar system and was warmed by the sun, solid hydrogen would have begun to sublimate from its interior. Because hydrogen is invisible to our telescopes when released this way, it would provide the necessary thrust without producing any observable coma. Another idea posits that the acceleration could have been caused by the breakdown of water ice by cosmic radiation deep within the object, creating pockets of hydrogen gas that were then released. While these are elegant solutions, they also require very specific and rare conditions for Oumuamua's formation, making it either a tremendous coincidence or an indication that such objects are far more common than we think. The bitter truth is that we will likely never know for certain what Oumuamua truly was. It is now far beyond the reach of our telescopes, speeding silently into the blackness of the interstellar medium, carrying its secrets with it. Its enduring legacy, however, is profound. It shattered our paradigm, proving that interstellar objects are not just theoretical constructs but tangible visitors, and that they can behave in ways that defy our immediate understanding. It was a test, and in many ways we failed. We were unprepared. Our instruments were not ready to get a detailed look at it before it vanished. This failure is now a driving force behind new mission concepts and telescope designs. Projects like the Lyra mission study, which proposed ways we could have chased it down, and the upcoming Vera-C, Rubin Observatory, which will scan the entire sky nightly, are direct responses to the Oumuamua event. They are being built precisely so that when the next interstellar traveler arrives, we will not be caught off guard. We will be waiting, ready to point every instrument we have at it, determined to solve the mystery Oumuamua left behind and finally understand the true nature of these messengers from the stars. But for all the violence and spectacle we've witnessed from dying stars and colliding galaxies, some of the universe's most powerful events are utterly silent, completely invisible to our eyes and traditional telescopes. They announce themselves not with light, but with ghostly, almost massless particles that pass through our planet and even our bodies by the trillions every second without us ever noticing. These are neutrinos, and for over a century they have been the key to unlocking one of astronomy's most stubborn mysteries, the origin of cosmic rays. These are not rays of light, but actual particles, protons and atomic nuclei, that bombard Earth from space at energies far beyond anything our most powerful particle colliders can produce. We've known they exist for decades, but their sources have remained hidden because their paths are bent and scrambled by magnetic fields during their immense journeys, erasing any trace of where they began. That all changed in a moment of breathtaking cosmic detective work. On September 22, 2017, an alert went out across the global astronomy community. A single, exceptionally high-energy neutrino had been detected by the IceCube Neutrino Observatory, a massive detector frozen deep into the Antarctic ice at the South Pole. This wasn't just another neutrino. Its extraordinary energy indicated it was a messenger from an extremely violent event, likely far beyond our galaxy. But a single direction, while helpful, isn't enough to pinpoint a source. The true breakthrough came from a follow-up call to action. Telescopes across the globe and in space swiftly pivoted to the coordinates IceCube provided, scanning the patch of sky for anything unusual. And there it was, a known object previously catalogued as a bright blazar was in the midst of a dramatic flare. A blazar is one of the most energetic phenomena in the universe. It is a supermassive black hole at the center of a galaxy, but with a terrifying twist. This black hole is actively feeding on immense amounts of material, and in the process, it fires out a pair of jets of radiation and particles at nearly the speed of light. A blazar is simply a galaxy where one of these deadly jets is pointed directly at Earth, like a cosmic gun barrel aiming right at us. This particular blazar, designated TXS0506+056, was located 4 billion light-years away, and it was screaming with activity. The correlation was undeniable. The neutrino and the gamma-ray flare were not a coincidence. They were different signatures of the same catastrophic event. This was the smoking gun. For the first time, we had definitively tied a neutrino, a neutral particle that travels in a perfectly straight line from its source, completely unaffected by magnetic fields, to a specific celestial object. This single ghostly particle, detected after traveling for 4 billion years, solved a 100-year-old mystery. It proved that the engines powering blazars are also cosmic particle accelerators of almost unimaginable power, capable of hurling not just photons of light, but also massive particles like protons across the universe. The process inside those relativistic jets is so violent that particle collisions must be constant, creating a maelstrom that forges both the high-energy photons we see and the neutrinos we can barely detect. The implications of this discovery are as profound as they are wide-ranging. It opens an entirely new window onto the universe, one we call multi-messenger astronomy. We are no longer just stargazers, we are now cosmic listeners, tuning into the universe through different messengers: light, gravitational waves, and now neutrinos. Each one tells a different part of the story. Light shows us the heat and fury of an event. Gravitational waves reveal the dance of massive objects, and neutrinos give us a direct, unaltered view into the heart of the particle acceleration process itself, from deep within the most powerful engines in the cosmos. This one detection didn't just solve an old puzzle. It inaugurated a new era of exploration, where a single, silent ghost particle can lead us directly to the most violent and spectacular factories of the universe. Imagine finding a world that has somehow survived its own apocalypse, a planet that by every rule of astronomy should have been stripped down to a barren, airless core billions of years ago. This is the bizarre reality of LTT 9779b, a planet that defies one of the most fundamental principles of astrophysics and has earned the title of the ultimate cosmic survivor. Discovered by NASA test mission orbiting a sun-like star 260 light-years away, this world is an ultra-hot Neptune, a gas giant roughly the size of our own Neptune but placed in a scorchingly close orbit. It completes a full journey around its star in a mere 19 hours, meaning its year is shorter than a single Earth day. At that distance, the planet is quite literally roasting, with its dayside temperature soaring to a staggering 1,700 degrees Celsius, hot enough to vaporize titanium. This is the heart of the mystery. According to everything we understand about planetary physics, a planet of this size and composition should not be able to exist so close to its star. We have a well-established category of planets called hot Jupiter's massive gas giants that can withstand the intense radiation of a close orbit because their enormous gravity acts like a powerful shield, holding onto their thick atmospheres against the stellar wind. On the other end of the spectrum, we find small, rocky worlds that have had their atmospheres completely stripped away, leaving behind nothing but a charred husk. LTT 9779b sits in the precarious middle ground we call the hot Neptune Desert, a region where planets of its size are almost never found. Its gravity is too weak to firmly hold onto its gaseous envelope, yet it has not been completely evaporated. It's like a massive ice cube sitting on the surface of the sun, stubbornly refusing to melt. So how does it survive? Astronomers believe the answer lies in a delicate and fascinating balancing act. The leading theory suggests this planet may have started its life much farther out in its solar system, a cold and icy giant in the frozen reaches beyond the frost line. A gravitational encounter with another planet, or perhaps the slow drag of a remaining protoplanetary disk, could have sent it migrating inward on a death spiral toward its star. As it drew closer, the intense stellar radiation began to blast its atmosphere away, creating a colossal, comet-like tail of lost gas. But here's where the plot twists. The planet might be losing its atmosphere at a rate that is just slow enough to be sustainable over billions of years. Its high metal content detected in its atmosphere suggests it could have an unusually large and massive core. This dense heart would provide a stronger gravitational anchor, making it harder for the star to pull the entire atmosphere away. Another compelling idea is that the planet's atmosphere is actively fighting back. The same intense heat that is trying to destroy it might also be creating a protective shield. The upper atmosphere could be superheated to a point where it forms a high-altitude layer of metallic clouds, possibly composed of metals like titanium or silicate minerals. Think of it as a planet-wide sunshade made of vaporized rock. These highly reflective clouds could be bouncing a significant amount of the star's destructive energy back into space, effectively putting up a parasol to slow down the rate of atmospheric evaporation. It's a brilliant, self-regulating defense mechanism where the very cause of its destruction also provides the means for its survival. The existence of LTT 9779b forces a complete re-evaluation of planetary resilience and evolution. It proves that our models of atmospheric escape are still incomplete, and that planets can find ingenious ways to endure in the most hostile environments imaginable. This lone world, blazing a path through the hot Neptune desert, is more than just an oddity. It is a crucial key to understanding the life cycles of planets. It shows us that the cosmos is full of exceptions to every rule, and that sometimes, against all odds, a world can stare into the inferno of a star and not just survive but stubbornly persist for eons. For centuries, the cosmic web existed only as a beautiful theory, a ghostly blueprint predicted by our most advanced computer simulations of the universe. These models showed a vast, interconnected network of dark matter filaments, a cosmic spiderweb stretching across the emptiness, with glittering galaxies forming at the nodes where these threads crossed. But to actually see it, to capture its faint light directly, seemed an impossible dream. That all changed with a monumental observation targeting a region of space containing the galaxy cluster MAX 0717. Using the powerful Keck Observatory in Hawaii, astronomers did not look for the dark matter itself. That remains invisible, but for the telltale signature of the gas that traces its outline. They focused on a filament stretching between two merging clusters, and by analyzing the light from distant background galaxies shining through this cosmic structure, they were able to map the hydrogen gas that had been heated and illuminated by the immense gravitational pull of the dark matter within. For the first time, we had a direct image, not a simulation, of one of the universe's fundamental skeletons. This was more than just a spectacular picture. It was a profound validation of our entire understanding of cosmic evolution. The existence of this web explains why galaxies aren't scattered randomly through the void like salt spilled on a table. Instead, they are strung along these invisible rivers of dark matter, flowing along the filaments toward the dense intersections where they gather into immense clusters. The cosmic web is the ultimate cosmic conveyor belt, the supply chain for galaxy formation. The dark matter filaments act as gravitational highways, funneling vast reservoirs of pristine hydrogen and helium gas, the raw material for building stars, from the empty voids toward the waiting galaxies. Without this constant replenishment, galaxies would have exhausted their fuel billions of years ago, and the universe would be a much darker place. This direct observation confirms that the web is not static. It is a dynamic, living structure, constantly channeling the flows of matter that shape the destiny of everything within it. The method used to see the unseeable is a testament to astronomical ingenuity. It relies on a phenomenon called fluorescence. Just as a blacklight can make certain paints glow, the intense ultraviolet light from pockets of furious star formation within the clusters was energizing the gas within the filament. This caused the hydrogen atoms to re-emit this energy as a specific wavelength of light known as Lyman alpha radiation. By using a custom-built filter on the telescope that isolates this exact wavelength, astronomers were able to effectively take a picture of just the glowing gas within the filament, subtracting the light from everything else in the field of view. It was like using a cosmic filter to see only the neon sign of the gas, revealing the intricate structure hidden in plain sight. This technique has opened a new window onto the large-scale structure of the universe, allowing us to begin mapping the distribution of matter not just in 2 dimensions, but in 3, charting the true architecture of the cosmos. Understanding the cosmic web is crucial to solving one of the biggest mysteries in galaxy evolution. What shuts down star formation? Galaxies in dense clusters are often red and dead, massive collections of old, red stars that have long since stopped producing new ones. The prevailing theory is that these galaxies have been cut off from their fuel supply. The immense gravitational tides within a cluster, or the searing heat from its superhot plasma, can prevent the cool gas from the cosmic web from flowing in and replenishing the galaxy. It's like a city whose main aqueduct has been severed, dooming it to eventually run dry. By studying how gas moves along these filaments and where it gets disrupted, we can finally understand the life and death cycle of galaxies on the grandest scale. The first direct images of the cosmic web are not an endpoint. They are the beginning of a new era of cartography, where we will finally map the hidden currents that have guided the growth of the universe since the dawn of time. But sometimes the most profound discoveries aren't made by algorithms or supercomputers. They come from the collective power of human curiosity, from thousands of volunteers scanning the heavens simply for the joy of it. This is the heartwarming story of the yellow balls, a new class of celestial object that was hiding in plain sight within the vast infrared archives of the Spitzer Space Telescope, just waiting for a human eye to finally see them for what they are. The project began with the Milky Way Project, a citizen science initiative on the Zooniverse platform that invited the public to help astronomers categorize and map the intricate structures of our galaxy. Volunteers were shown images from Spitzer and asked to draw circles around bubbles, the beautiful shell-like structures carved out by the fierce radiation and stellar winds from massive young stars. It was during this meticulous process that volunteers started noticing something the professional astronomers had overlooked. Scattered among the bubbles were small, compact, and distinctly yellow objects. They didn't fit the definition of a bubble, so the volunteers began marking them with the simple comment, "yellow ball." At first, the research team running the project assumed these were just image artifacts or glitches, perhaps even errors made by the volunteers. But the comments kept coming in from hundreds of different people, all independently identifying the same strange features. The consistency was impossible to ignore. The scientists had to admit that their citizen scientists were onto something truly novel. These yellow balls were real, and they represented a critical, previously unnoticed stage in the life cycle of stars. So, what exactly is a yellow ball? In the infrared eye of the Spitzer telescope, which sees the heat radiation from cosmic dust, color is a direct indicator of temperature. The now famous 3-color images assign blue to light emitted at 3.6 microns, primarily from stars. Green represents warm dust at 8 microns, often tracing complex organic molecules. And red signifies hot dust at 24 microns, which is heated by the most energetic processes. A yellow ball appears yellow because it is a compact, balanced mix of all three. It is a dense, dusty cocoon that is simultaneously hosting the birth of new stars while still shrouding them in the thick, natal material from which they formed. They are essentially stellar nurseries caught in the act of turning on, a fleeting moment in cosmic time that lasts perhaps only a few 100,000 years. The significance of this discovery is enormous. Yellow balls appear to be the missing link between two major phases of star formation. They are the immediate precursors to the bubble structures the volunteers were originally looking for. A yellow ball represents the stage when a cluster of massive stars has just begun to ignite. Their radiation is heating the surrounding dust and making it glow, but they haven't yet grown powerful enough to blow away their birth cloud and carve out the clear, empty cavity of a bubble. By studying the properties of thousands of these yellow balls, astronomers can now track the earliest moments of a star cluster's evolution, understanding how they heat their environment and eventually break free to become the dominant forces in their region of the galaxy. This story is a powerful testament to the unique capabilities of the human brain. Our pattern recognition skills, our intuition, and our ability to spot anomalies that don't fit a predefined category are still unmatched by even the most sophisticated algorithms. The volunteers weren't just clicking buttons, they were actively participating in the scientific process, bringing their own curiosity and perception to a massive dataset and seeing something new. They moved from being passive observers to active contributors, their collective curiosity directly leading to a formal classification in astrophysical literature. The yellow balls are a beautiful reminder that the universe still holds surprises, and that sometimes you just need a fresh pair of eyes or 10,000 of them to look at the sky and ask a simple, wonderful question: what's that yellow thing? While planets and moons often steal the spotlight, some of the solar system's most profound secrets are guarded by much smaller, quieter inhabitants. Leading the way in its long journey around the Sun, Jupiter is not traveling alone. It is flanked by two vast swarms of ancient asteroids, known as the Trojan asteroids, which orbit in a stunning, gravitational dead zone created by the perfect balance between the Sun's pull and Jupiter's own immense gravity. These rocks are trapped in what are called Lagrange points, specific regions where the gravitational forces and the orbital motion of a planet create pockets of stability. Jupiter's leading swarm, known as the Greek camp, orbits 60 degrees ahead of the planet, while the trailing swarm, the Trojan camp, follows 60 degrees behind. From the perspective of Jupiter, these asteroids appear to march in a perfectly synchronized eternal parade, never falling behind and never racing ahead, locked in a celestial dance that has lasted for billions of years. For a long time, these Trojan asteroids were little more than faint points of light, their true nature hidden by distance. But recent observations, particularly from NASA's Lucy mission, which is on its way to study them up close, and powerful telescopes like the Keck Observatory, have begun to peel back the layers of mystery. Astronomers have been able to analyze the light reflected off these distant worlds, a technique called spectroscopy, and the results have been startling. A significant number of these asteroids are incredibly dark and red, much darker than a blackboard, and with a deep red tint that suggests a surface rich in complex organic compounds, the very building blocks of life. This composition is eerily similar to what we see in the Kuiper Belt, that distant realm of icy objects beyond Neptune. This is a monumental clue because it suggests these asteroids did not form anywhere near Jupiter's current orbit. They are RE Chinese letter, invaders from the outer solar system that were captured during a period of immense upheaval. This is where the story of the Trojans becomes the story of our entire solar system. Their existence and their composition are considered some of the strongest evidence we have for the Grand Tack hypothesis, a dramatic model of our solar system's early history. This theory proposes that in its first few million years, Jupiter did not form and simply stay put. Instead, it embarked on a grand migration. The young gas giant, once formed, began to drift inward toward the Sun, its gravity clearing a path through the primordial disk of gas and dust. It might have gotten as close as the orbit of Mars is today, threatening to become a hot Jupiter and utterly disrupt the inner solar system. But then Saturn formed. As Saturn grew, its own gravity began to interact with Jupiter's, creating a kind of gravitational tug-of-war. The two giants became locked in a resonant orbital dance that halted Jupiter's inward death march and pulled them both back outward to their current positions. This planetary migration was a chaotic event that reshaped the entire solar system. As Jupiter swung back out, its immense gravity acted like a fishing net, scooping up a vast population of these primitive, dark, organic-rich objects from the Kuiper Belt region and flinging them inward. But rather than being consumed or ejected, a fraction of this captured material found sanctuary in the stable Lagrange points, becoming the Trojan asteroids we see today. They are frozen relics of that violent epoch, a preserved sample of the building blocks that formed in the cold, dark outer solar system billions of years ago. By studying them, we are effectively conducting an archaeological dig on the solar system's earliest days, examining material that was transplanted during its most dynamic period of planetary rearrangement, giving us a direct window into the conditions that existed far from the sun's heat and light. Now, just as we map the cosmic web that shapes the universe on the grandest scale, we must also confront the force that threatens to tear it all apart. For the past 2 decades, our standard model of cosmology has been built upon a bedrock of two mysterious, invisible components: dark matter, which sculpts and holds the cosmos together, and dark energy, a repulsive force that is pushing it apart at an ever-increasing rate. The discovery of dark energy's accelerating expansion was a Nobel Prize-winning revelation, one that seemed settled. But new data from the monumental Dark Energy Survey is now shaking that foundation to its core, suggesting our understanding of this dominant force might be fundamentally flawed. The entire endeavor hinges on a specific kind of stellar explosion, Type 1, a supernova. These aren't just any supernova, they are what astronomers call standard candles. This is because the physics behind them is so uniform. They occur in binary systems where a white dwarf star steals material from a companion. Once the white dwarf accretes enough mass to reach a very specific threshold, about 1.4 times the mass of our Sun, a runaway thermonuclear explosion ensues, obliterating it completely. Because this detonation always happens at the same mass limit, the intrinsic brightness of these explosions is incredibly consistent. They are like cosmic light bulbs of a known wattage. By measuring how bright they appear to us here on Earth, their apparent brightness, astronomers can calculate with remarkable precision how far away they are. It's like seeing a known candle flame from across a field. The fainter it appears, the farther away you know it must be. But these supernovae do more than just tell us distance. They also reveal the expansion history of the universe itself. As the light from a supernova travels across billions of light years to reach us, the expansion of space stretches the wavelength of that light, shifting it toward the red end of the spectrum. By measuring this redshift and combining it with the distance gleaned from the supernova's brightness, scientists can trace how fast the universe was expanding at different points in its history. It was precisely this technique that first revealed the shocking acceleration of the cosmos in the late 1990s. The distant supernovae were significantly dimmer than expected, meaning they were farther away than they should have been if the universe's expansion were constant or slowing down. Something was pushing galaxies apart faster and faster over time. That something was dubbed dark energy. The Dark Energy Survey, or DES, was conceived to take this profound discovery and put it under a microscope. For 6 years, using a 570-megapixel camera mounted on a telescope in Chile, it meticulously mapped hundreds of millions of galaxies and discovered thousands of these crucial Type 1a supernova. The goal was to measure the properties of dark energy with unprecedented precision, to determine if its strength has remained constant over time, as the simplest model, Einstein's cosmological constant, suggests, or if it has varied. The parameter used to describe this is called W, the equation of state for dark energy. If W is exactly -1, it means dark energy is constant and unchanging, a permanent fixture of the vacuum of space itself. The initial results from DS, however, are pointing in a different, far more provocative direction. After analyzing the first 3 years of supernova data, the team found a value for W that is not -1 but slightly different. The uncertainty in the measurement means it could still be consistent with the standard model, but the hint is tantalizing and troubling. It suggests that dark energy might not be constant after all. It could be dynamic, evolving, and weakening over the history of the universe. This is a seismic suggestion. If dark energy's strength has changed, it means our simplest and most elegant model for it is wrong. Einstein's cosmological constant, a concept he once called his greatest blunder, might have been right all along, but this new data implies the truth could be even stranger. This creates a major controversy in cosmology because the DS supernova findings don't exist in a vacuum. They must be reconciled with other powerful probes of the universe, like the cosmic microwave background radiation measured by the Planck satellite. The Planck data, which provides a baby picture of the universe, strongly supports a constant dark energy model with a W of -1. The two most precise experiments ever conducted to understand the cosmos are now whispering two different stories about its ultimate fate. One possibility is that there is a hidden systematic error in one of the measurements, perhaps in how we're calibrating the brightness of the most distant supernova. The other, more thrilling possibility is that we are seeing the first cracks in the standard cosmological model, hints of new physics that we have not yet begun to comprehend. If dark energy is indeed dynamic, it forces us to consider origins for it that are far more exotic. Perhaps it is not a property of space itself, but a new type of field that permeates the cosmos, a cousin to the Higgs field that gives particles mass but with repulsive gravity. Theorists call this concept quintessence, a fluid-like energy that can change density and strength over time. Or perhaps our understanding of gravity itself is incomplete on the largest scales, and Einstein's theory of general relativity needs a modification. The DS findings are not a conclusion. They are an invitation to a much deeper mystery, a signal that the universe's greatest energy source, which makes up nearly 70% of everything that exists, is even more enigmatic than we dared to imagine. And now we turn from the grand, cosmic-scale mysteries of dark energy to a world that is the very definition of a personal hell, a planet so violently active that its entire surface is quite literally on fire. Meet Toy 6713. 01, an exoplanet that redefines our understanding of geological extremes. Located about 66 light-years away, this world is slightly larger than Earth, but any similarity to our home ends there. Observations from NASA's Transiting Exoplanet Survey Satellite, or TESS, revealed its presence by the telltale, periodic dimming of its host star, but the data held a far more intriguing secret. When astronomers analyzed the light from the star as it filtered through the planet's atmosphere during these transits, they found something astonishing. The secondary eclipse, the dip in light that occurs when the planet moves behind its star, was far deeper than anyone expected. This meant the planet wasn't just absorbing and reflecting its star's light. It was also emitting a tremendous amount of its own heat, glowing with an intense, furious redness all on its own. The source of this incredible heat isn't a nearby sun, but the brutal and unrelenting gravitational tug of war it experiences from its own star. Toy 6713. 01 is part of a compact, multi-planet system where the worlds are locked in a delicate orbital resonance, meaning their orbits are synchronized in a precise ratio that amplifies their gravitational influence on one another. As this planet travels along its highly elliptical or egg-shaped path, the star's gravity squeezes and stretches it dramatically. This process, known as tidal heating, is the same phenomenon that keeps the interior of Jupiter's moon Io molten, making it the most volcanically active body in our solar system. But in the case of TOI 6713-01, the effect is magnified to an almost unimaginable degree. The tidal forces acting upon it are orders of magnitude more powerful, essentially kneading the planet's interior like a ball of clay, generating immense friction and heat from the very core outward. The result is a global inferno. Current models suggest that the entire surface of TOI 6713-01 is likely covered in erupting volcanoes, with vast rivers of lava carving channels through a crust that is constantly being shattered and remade. Its temperature is estimated to be around 2,600 degrees Celsius, which is hotter than some stars and certainly hot enough to melt rock and metal into a global ocean of magma. There is no solid ground, no stable geology, only a perpetual, churning cauldron of superheated liquid stone. The planet is essentially turning itself inside out, with its internal heat being violently vented into space through countless volcanic vents and fissures, causing it to glow with its own sinister light against the blackness of space. This nightmarish world offers a terrifying glimpse into the potential fates of planets caught in gravitational traps. It serves as a crucial natural laboratory for understanding the extreme limits of tidal heating and planetary dynamics. By studying its orbit and its intense thermal signature, astronomers can test and refine their models of how orbital resonances can pump energy into a world, ultimately determining whether it becomes a temperate haven or a scorched wasteland. TOI 6713-01 stands as a stark warning about the violent mechanics of solar systems, proving that a planet's orbit can be just as important as its composition in deciding its destiny. It is a monument to cosmic chaos, a world where the very forces that bind the universe together have conspired to create a perpetual, globe-spanning volcanic apocalypse. Yet for all the extreme conditions we've catalogued, from the self-immolating surface of TOI 6713-01 to the ghostly neutrino factories of distant blazars, one fundamental force has been a silent partner in the evolution of nearly everything: magnetism. It is a universal presence, from the humble fridge magnet to the vast, galaxy-spanning fields that guide the collapse of gas clouds and the birth of stars. We've long assumed that these colossal magnetic fields were a product of time, slowly amplified over billions of years by the churning dynamos of spinning galaxies and collapsing stellar cores. This entire framework of a universe where magnetism grows stronger with age has just been confronted with an object that simply should not be. In the distant, early universe, we've found a quasar that is a magnetic monster, a brilliant beacon whose immense power is fueled by a magnetic field of staggering strength that defies every timeline we have for how such forces emerge. This object, a quasar known by the catalog number SDSSJ 1030+0524, is not just any active galaxy. We are seeing it as it was a mere 1.5 billion years after the Big Bang, a toddler in cosmic terms. At its heart lies a supermassive black hole furiously consuming matter, blazing with the light of millions of stars. But it's what's happening around this black hole that has left astrophysicists reeling. By analyzing the subtle properties of its light, specifically a phenomenon called Faraday rotation, astronomers were able to measure the strength of the magnetic field threading the quasar's brilliant disk of hot gas. The value they found was breathtaking, a field of over 1 Gauss, potentially even several Gauss, permeating the structure. To put that in perspective, that is thousands of times stronger than the Milky Way's average magnetic field, and our galaxy has had over 13 billion years to build its magnetism through the slow, constant rotation of its spiral arms. This quasar achieved a similar, if not greater, strength when the universe was less than 15% of its current age. This discovery throws a massive wrench into our established models of magnetic field growth, which are built on a concept called a dynamo. The standard theory is beautifully simple in principle. Start with a tiny seed magnetic field, perhaps generated by the movement of charged particles in the early universe. Then take a massive object like a galaxy disk and set it spinning. This motion, combined with the complex turbulence of gas and plasma, acts like a gigantic amplifier, stretching and twisting those weak seed fields, winding them up over immense timescales until they become the powerful forces we observe today. It's a process that is supposed to be slow and gradual, requiring multiple rotations of a galaxy to reach significant strength. SDSSJ 1030 plus 052 foreshadows this leisurely timeline. It presents us with a magnetic field that is already fully mature, a cosmic giant in its infancy, leaving us with a profound puzzle. How did it get so strong so fast? The implications of this are monumental, reaching far beyond the quasar itself and into the very heart of how galaxies evolve. Magnetic fields are not mere cosmic decoration, they are active, influential players. They provide pressure that can support gas clouds against gravitational collapse, they accelerate particles to near light speed, and they regulate the flow of material onto growing black holes and into forming stars. A magnetic field this powerful, present so early on, would have had a dramatic impact on its host galaxy. It could have turbocharged the growth of the central black hole by efficiently funneling gas inward, and it would have exerted a powerful influence on the earliest generations of star formation, perhaps leading to stars that were more massive or formed in a different way than in galaxies with weaker fields. This single object suggests that the seeds of magnetism were not weak and primordial, but potentially strong and generated by dynamic processes we are only beginning to understand. So what could have created such a powerful field in such a short time? Astronomers are now forced to consider far more rapid and violent mechanisms. One compelling possibility involves the intense turbulence and shear forces present in the accretion disk around the newly formed supermassive black hole itself. The incredible energies at play, with gas swirling at near light speed and slamming into itself, could have acted as an ultra-efficient, fast dynamo, amplifying a weak seed field to enormous strengths in a relative blink of an eye, on the order of millions of years instead of billions. Another theory looks to the jets themselves, proposing that the processes that launch these colossal beams of matter might also be inherently capable of generating immense local magnetic fields that then flood back into the galaxy. Whatever the cause, this magnetic monster stands as a stark challenge, forcing us to rewrite the early chapters of cosmic history to include a new, powerful character whose influence shaped the universe far sooner than we ever thought possible. Yet for all the immense scales and violent forces we've explored, from colliding galaxies to the very fabric of the cosmic web, some of the universe's deepest mysteries operate on a scale so small it defies everyday intuition. This final oddity brings us to the bizarre and counterintuitive heart of quantum mechanics, a realm where logic seems to break down and particles can become linked in a way that Einstein himself famously dismissed as spooky action at a distance. This phenomenon is quantum entanglement, and recent experiments conducted in the vacuum of space have not only confirmed its reality over record-breaking distances, but have also opened the door to technologies that once belonged solely to the domain of science fiction. To grasp why entanglement is so profoundly strange, imagine a simple experiment with two particles, let's say, two photons of light. If these photons are created together in a certain way, they can become entangled, their properties inextricably linked. Now send one of these photons to a lab in Beijing and the other to a lab in Vienna. The bizarre quantum rule is this: the properties of each photon, such as its polarization, are not fixed until the moment they are measured. But here's the spooky part. The instant you measure the photon in Beijing and force it to choose a state, its entangled partner in Vienna, thousands of miles away, immediately assumes the corresponding state, no matter how much distance separates them. This connection appears to happen faster than the speed of light, a notion that seems to violate the fundamental cosmic speed limit set by Einstein's theory of relativity. This is what so troubled Einstein. He believed this implied that quantum mechanics must be incomplete, that there must be some hidden variables, unknown properties that predetermine the particle states all along, making the illusion of instantaneous communication just that, an illusion. For decades, physicists debated this, but they lacked a way to test it definitively on a grand scale. The solution came from a physicist named John Bell, who devised a cunning theorem that could, in principle, settle the argument. Bell's inequality provides a mathematical way to distinguish between Einstein's hidden variables and true spooky action. If experiments violate Bell's inequality, then Einstein was wrong and entanglement is real. This is where space itself became the ultimate laboratory. On Earth, conducting such an experiment over long distances is incredibly difficult because photons sent through fiber optic cables get scattered and absorbed by the material, limiting how far they can travel before the delicate quantum link is lost. The solution was brilliantly simple: go above the atmosphere. In 2016 and 2017, a team of Chinese scientists used their Misha satellite, a sophisticated quantum optics lab orbiting 500 kilometers above the Earth, to perform a series of landmark experiments. They created pairs of entangled photons on the satellite and then beamed them down to two separate ground stations in China that were over 1,200 kilometers apart, a distance far greater than any achieved on Earth. The results were unambiguous and breathtaking. The photons arrived at the ground stations and their properties were measured simultaneously. The correlation between them was so strong that it violated Bell's inequality by a huge margin. There were no hidden variables. The spooky action was real. The instant measurement of one photon truly did dictate the state of its partner, even across a distance that would take a light beam 4/1000ths of a second to cross. This wasn't just a parlor trick, it was a monumental test of the foundations of quantum mechanics, proving that this strange interconnectedness is a fundamental feature of our universe, one that operates seamlessly across planetary scales. But confirming a century-old theory is only half the story. The other half is about building a future that seems ripped from the pages of a novel. This successful demonstration of space-based quantum entanglement is the foundational step toward a completely new kind of internet, a quantum internet. Unlike our current internet, which can be eavesdropped on, a quantum network would be inherently secure. The reason lies in the very nature of measurement in quantum mechanics. Any attempt to intercept or measure a quantum message would unavoidably alter its state, immediately alerting the sender and receiver to the presence of an intruder. This principle allows for quantum key distribution, where two parties can generate an unbreakable secret key for encrypting their messages because they would know with certainty if anyone had tried to listen in. The Misha satellite has already demonstrated this, facilitating the first intercontinental quantum secured video call between China and Austria. By entangling photons and sending them to these distant continents, the team generated cryptographic keys that were secure from any possible interception. This is not just an incremental improvement in security, it is a paradigm shift. It promises a future where financial transactions, government communications, and personal data could be protected by the fundamental laws of physics themselves, rather than by mathematical algorithms that could one day be broken by a powerful enough computer. Looking even further ahead, this technology could do more than just secure our emails. It could link together future quantum computers into a powerful network. Just as the regular internet allows classical computers to share information, a quantum internet would allow quantum computers to share quantum states, creating a distributed processing power that is almost impossible to conceive of today. This could accelerate discoveries in medicine, materials science, and artificial intelligence in ways we are only beginning to imagine. The experiments with missions are the hesitant first steps into that new world, proving that the vacuum of space is not a barrier to quantum technologies, but rather the perfect medium for them. It shows us that the universe at its most fundamental level is deeply interconnected, and that by embracing the spookiness, we might just unlock the next revolution in how we communicate and compute. From the rogue black holes farming newborn stars to the impossible magnetic fields of the early cosmos, these 30 discoveries are far more than a simple catalogue of cosmic trivia. They are a powerful testament to a single, humbling truth: the universe is fundamentally, profoundly, and magnificently weirder than we ever dared to imagine. Every time we think we've got it figured out, the cosmos delivers another paradox, another lawbreaker, another whisper from the void that forces us back to the drawing board. These oddities are not failures of our understanding. They are the very engine of discovery, each one a signpost pointing toward a deeper, more complex reality waiting to be uncovered. This relentless cycle of mystery and revelation is the true heartbeat of science. We build a model, a framework that explains everything we see, and for a moment it feels complete. Then along comes a galaxy with no dark matter, a planet that stubbornly floats where it should evaporate, or a particle that communicates across continents instantaneously, and that beautiful, comfortable model shatters. In its place, we're left with a more fascinating, more confusing, and ultimately more exciting puzzle. The greatest discovery isn't finding an answer, it's realizing the question was far better than we thought. These 30 space oddities are 30 such questions, each one an invitation to dream bigger, think stranger, and explore further. So the next time you find yourself under a clear night sky, take a moment to really look up. Remember that the darkness between the stars is not empty. It's a frontier teeming with impossible planets, invisible structures, and forces that defy our very laws of physics. That sense of wonder you feel isn't just poetry, it's the starting point of every great discovery. Nurture that curiosity, question what you think you know, and never stop being amazed by the sheer, bewildering creativity of the cosmos we call home. Now we want to hear from you. Which of these 30 oddities completely rewired your brain? Was it the ghostly signature of a collision with another universe in the Great Cold Spot, the terrifying global lava ocean of TOI 6713-01, or the spooky quantum connection that could one day power an unhackable internet? Share your favorite cosmic head-scratcher in the comments below and tell us why it captured your imagination. The conversation is just beginning, and the universe, as we've seen, has no shortage of secrets